Today, Alex is going to be talking about string diagrams for the surface code. So,
Hiya. Thanks for inviting me. So I'm going to be talking about, oh, it sounds like someone's got their mic on, so I'm getting feedback. I'm going to be talking about string diagrams for the surface code. The surface code is a lattice-based topological way of encoding quantum information so that it's error corrected up to some threshold. But the reason why I'm giving that brief description now is because throughout the talk, I'm actually not going to be referring to the lattice or to the physical features of the surface code in any detail. The point of this is to try to take a top-down kind of algebraic view of the operations, the logical operations that are being performed, and abstract away the underlying lattice. So in order to do this, we're going to introduce some categorical stuff. Because I'm aware that the audience is kind of a bit of a mixture, I'm going to try to prune back the categorical baggage, and I'm going to try to do things as diagrammatically as possible. So we're going to start off with, we have some object in our category, which we're representing as a string, as a line, and a physical interpretation for modular tensor categories is that this object is some particle or composite of particles which is traveling through space-time. So we have a time-like direction going from left to right, and we then have morphisms which act on this object, which we're representing as boxes or other such kind of sub-diagrams, which you'll see throughout the talk. And this is acting on the particle or a set of particles in some manner. The category is monoidal, meaning that it has a monoidal product, which you can physically interpret as particles can sit next to each other in parallel. And it is also equipped with cups and caps, i.e. duals. The interpretation here would be that you can generate a particle, but when you do so, you also generate the antiparticle. As it turns out, for all the cases that we consider, the objects are self-dual, so we don't need to draw arrows or anything like that to denote the difference between particles and antiparticles. So you can initialize some system by creating a particle and antiparticle, and you can measure out some system by annihilating an antiparticle and a particle. These duals obey the snake equations, and in addition, we are equipped with some braiding, and this is kind of a braiding of the world lines of the particles that we're going to be considering. And these are going to be pretty important in order to perform computation. Okay, so I'm going to try to not talk about this too much, but the category is also abelian, which means that we have finite byproducts for any objects in our category. And you can think of this as being kind of a superposition rule. So you could have some particle which you don't know whether it is a particle of type A or particle of type B. We also have a zero object, which you can think of as being an impossible state for the system to be in. And because this object is both initial and terminal, there is a unique morphism which factors through this object, which you can think of as being a transition in between states, which is also impossible. And we have so-called simple objects. Categorically, this means that for a simple object is defined as any morphism which is going to a simple object is either an isomorphism or a I can't remember what the other one is, but a physical interpretation of this is that a simple kind of atomic object or particle can't be broken down into even more atomic pieces. And this is going to be useful because our category is semi-simple. So this means that any object in our category is isomorphic to some byproduct of simple objects. So any composite that we can construct out of our particles is in some superposition of simple particles. In the cases that we're going to be looking at, this set is also finite. So everything is some finite byproduct of simple objects. In particular, this means that we have so-called fusion rules. So if we have any two objects, then we can fuse them together into the corresponding superposition of simple particles. And through the kind of morphisms and objects that I've shown you so far, you can build up larger diagrams, diagrams like this. Okay, so let's add a bit more structure. So our category is C-linear, meaning that the Hom sets of the category are actually vector spaces over C, which leads to a slightly kind of confusing interpretation at first glance, because this means that a morphism between two objects, which exists in this Hom set or Hom vector space, is a vector, which you could think of as being kind of an unnormalized quantum state, which seems like the kind of opposite of what you want to be achieving here, because you have some quantum system which you're evolving over time. So surely you expect the evolution to correspond to linear maps rather than states. And we'll come back to that in a bit. Lastly, we have that the monoidal unit, empty space, the vacuum, whatever you want to call it physically, is simple.
Where are these milestones going to be put down? Is it confluence, somewhere where we can see them? Or do we...
Hello? I don't know if that was intended for me. So the unit, the vacuum is simple, and the endomorphisms on any the Hom set of endomorphisms.
Other task.
Konstantinos, your mic is on.
Yeah. Well, which task was it?
Huh? Ask the question again.
I think his mic is unmuted, but whoever started this meeting should be able to mute him, I think.
Okay, I'm going to just continue. So the endomorphisms on any simple object correspond to C. And so we won't be using this last piece of structure, but the category is also pivotal. In fact, it's a ribbon category, but I'm just going to mention that in passing. We don't really care about that for our purposes. Okay, so overall, we are kind of slowly adding more structure to reach a modular tensor category. The most important part of the modular tensor category is this modularity matrix at the bottom, but we for any given object, we have the dimension of the object defined as a cup, the identity, and then a cap at the top. The dimensions of the objects matter to determine how much quantum information you can encode in them, which I will get to. And the modularity matrix is the same matrix which pops up in quantum field theory. And it's a constraint which lets you relate some quantities which are quite useful. But again, I'm not going to be showing those calculations explicitly. Okay, so how do we encode information if it's not through the just the enrichment that I showed before? Well, we have some interpretation functor, which is in fact a representable functor, if you don't know what that is, that's fine, where we take any object to the finite byproduct of the vector spaces corresponding to the simple object and itself. So because this is a finite byproduct of complex vector spaces, this is also a complex vector space. So we've successfully taken the object, i.e. a state in this system, and mapped it to a vector space, which is where we would expect it to be. And the morphisms are now successfully mapped to linear maps. I'm getting notifications in the side, but I can't open them unless I close the presentation. So if it's important, then just interrupt me. Okay. Obviously, you can have, there are kind of a menagerie of different functors you could have from a modular tensor category to the category of vector spaces. So there's some reasoning behind why this is the correct one, but I'm not going to go into that either. Okay, so we now have braids correspond to linear maps. Empty space corresponds to complex numbers. And in particular, we have that the byproduct of any two simple objects corresponds to C2, i.e. qubits. And the more general byproduct corresponds to more general sized complex vector space. Okay, so having gone through all of that, I want to talk about the surface code, but given a slightly unusual presentation. So again, I'm not going to talk about the lattice or anything like that. So the surface code can be described by a modular tensor category where we have 4 simple objects, the vacuum, and then electric, magnetic, and epsilon, which satisfy the fusion rules below. In particular, some stuff that you can notice about this is that the fusion algebra is entirely deterministic. So unlike a slide I showed a wee while ago, where the fusion gave some non-trivial byproduct on the right-hand side, all of the right-hand sides here are just a single simple object. This means that you can't encode information in simple objects in the tensor product of simple objects, right? Because the interpretation functor will take everything through to just a tensor product of complex numbers. And so you have to add a bit more stuff to the surface code in order to encode information and to do quantum computing. And something else that you can notice from this is that if you ignore scalars, then the fusion algebra is the same as the algebra of the Pauli group, taking the tensor products to be the group operation. And this is in fact because for people who are aware of the lattice, E, M, and epsilon correspond to X, Z, and Y Pauli strings correspondingly. Okay. So we're going to encode information with byproducts rather than with tensor products of simple objects. And there's going to be 2 different encodings we're going to use. We're going to use a primal encoding, which is 1 plus E, which we're going to have as a cyan string, and the dual encoding, which is 1 plus M, which can be a black string. And this coloring is to coincide with Reusendorf's and some other people's from a while ago. And if we require to use simple objects, then we'll use a very thin string here to denote them. Okay, so at first glance, it appears that you can encode a qubit with just a single cyan line, right? You have 1 plus E, which corresponds to 2-dimensional vector space, where you have qubits. But sadly, it's not that simple. And the reason that it's not that simple is because of a kind of engineering constraint rather than a mathematical one. And the engineering constraint is that when you want to initialize or measure out these particles, you want to know beforehand and restrict yourself beforehand that you'll be able to initialize them from the vacuum, i.e. your computer will be able to start from a 0 state, well, a 1 state if you like, and generate computation. And at the end of your computation, you'll be able to measure everything out and and complete it and move on to something else, which means that that at the start and at the end, you want to have everything being in the one object, the vacuum state, and that means that you can't encode information which you're going to then measure out in subspaces corresponding to non-one objects. So above here we have 1 plus e tensor with 1 plus e, and this gives you a 4-dimensional vector space, which seems like too much, but at the point where you measure out, you can't have any non-trivial information in the e subspaces. This is called leakage if you do, and meanwhile, you will use these spaces for scratch space. So you use these spaces to perform computation, but then it has to be reset to 0 after you've performed said computation. So that's a lot of words, and I'm going to try and show that explicitly. You have the same phenomenon for dual qubits, where you're encoding a qubit in two dual objects. So on the left-hand side here, we have the initialization of 2 qubits using both primal and dual objects, and on the right-hand side we have the state which we're taken to by the interpretation functor, but this is modulo some the byproduct of some extra subspaces which are no computation is happening in. So we can then perform. We can get to the 1 state, and we can perform Pauli operations using some morphisms involving simple objects. Note that even though the simple objects can't encode any information themselves, they can still be used to perform maps on other quantum information which is stored. And we can do similar things using loops. And now we get to entangling, which is more interesting. So a C0 can be performed by braiding a 1 plus E object through a 1 plus M object and back out the other side. The reason why this is a kind of complete, quote unquote, complete braid, i.e. we're braiding under then back over again, is that if you only do half of it, then you'll end up with leakage. And therefore the maps that you make will not be, you won't be able to compose them to perform computation which is still guaranteed to be leakage free. So again, there is some extra byproduct of trivial stuff on the side here. This braid can be performed either clockwise or counterclockwise, and we still get the same information out. However, you can't braid the same object together either way. We can perform post-selection. Well, okay, in our model, we're going to perform post-selection by taking the dual, the caps. And again, this has some byproduct of extra stuff on the side. And obviously in practice, you can't actually perform post-selection. You have to measure out. And I'll get to that in a bit, but for now, we're going to assume that we can perform post-selection for convenience. By composing the objects and the morphisms from before, we can construct larger systems. So here we have an example of you want to perform a C0, but you start off with 2 primal qubits. You can perform this C0 by introducing an ancilla in the middle and braiding everything through. In a little bit, we'll prove why this is the case, that you can do this, but it's pretty straightforward. Something that I want to talk about a little bit here is the fact that, so the interpretation functor from the surface code modular tensor category to the category of finite vector spaces is strong monoidal. But clearly, because we have this additional constraint of trying to zero everything out of the extra subspaces, not only is this functor kind of, for all practical purposes, not strong monoidal, because everything has to be divided neatly into choices of qubit subspaces beforehand. But it's not even in practical terms functorial, because here we're just providing kind of partial maps, right, from left to right. Again, if you do a half braid, then you end up with non-trivial maps in the extra subspaces. Okay. Rather than talk about the other 1-qubit gates which you require to reach universal computation, so in particular T-gates, other Cliffords, I'm just going to leave these as boxes. So on the left-hand side, we have a dual qubit, which is having some operation, undefined black box operation performed to do a Z rotation. The reason why I'm not talking about this in any detail is because there are quite a lot of different methods for doing so, and lots of them require either knowledge of the lattice or different categories or yeah, things of that nature. So I promised string diagrams, and here are some more string diagrams. So rather than reason about our computation using the circuits which I initially introduced on the right-hand side, instead we're going to talk about them using ZX diagrams. So I assume that everybody here is fairly familiar with ZX diagrams and the ZX calculus, so I'm not going to spend too much time on this. We have some Z spiders with the corresponding linear map on the right-hand side. We have some X spiders, and we have a definition of a Hadamard, which you can decompose using Euler decomposition. They have some associated rules. Here I'm using the scalar free version because I'm not concerned about non-zero scalars. I couldn't convince myself to draw this out in Paint. And now we can replace all of the descriptions of our computation using ZX diagrams. So we have the initialization of a primal qubit going to a red spider, the initialization of a dual qubit going to a green spider. The C0 is now this thing on the right. And now we have the primal C0 from before. You can, by composing the individual pieces, you have the ZX diagram on the right here. But this is extremely straightforward to use first the merge rule to merge together all possible spiders of the same color, and then the identity rule to get rid of spare obsolete spiders. And we show that this is indeed a C0 from before. We can also perform type exchanges between the primal and dual qubit types, which is identity modulo the measurement which we have to perform, and fan in and fan out gates, which are essentially generalized C0s, where rather than just braiding around a single dual qubit, we're braiding around some finite number of them. And the same for the complementary type. And there's a whole screed of other easy conversions which I've put in the accompanying paper that I'm writing. But we're now going to move on to measurement. So rather than just post-selecting we want to perform, or we can in practice only perform measurements which give us some some unwanted Pauli's occasionally. And an example of this happening is when you want to perform fusion. So if you have two primal qubits, you can fuse them together just by stacking monoids on top of each other here. And this results in the linear map which you see on the right. Well, I guess the CPTP map that you see on the right. And in particular, you end up with a potential Pauli that you can induce on one of the wires. For anybody who's familiar with lattice surgery, this is exactly the same as a merge. There's the merge maps you get there, and indeed the Pauli is induced on the same on whichever wire you define as being the parent, which is just a matter of convention. And you have the complementary type here. Okay, so I've given kind of an example, a kind of zoo of lots of different conversions from these kind of particle operations to quantum operations represented in the ZX calculus. But in practice, what we actually want to do is the opposite. We want to start off with some representation of the operations that we want to perform. Sorry, the quantum operations we want to perform, the linear maps, the computation, and we want to compile that down to the surface code and end up with morphisms in the category. So naively, one could go about taking each quantum gate, finding some conversion for this, and then just emplacing the surface code operations. So here you'd have the problem with this circuit that you want to have C-naughts on which you require the qubit to be both a control of a C-naught and the target of another C-naught. And bearing in mind the definition of the braid which performs the C-naught, you will require extra type exchanges between different gates just in order to maintain the ability to perform C-naughts correctly. And even if you add in Hadamard's to swap the directions of the C-naughts, you're going to end up with the same problems on this circuit in particular, and many others. So you kind of have this this question of how can we bypass this in order to perform braids efficiently to perform the computation which we want. And efficiently, I mean raw numbers. I don't mean kind of complexities or anything like that. And the basic idea which a few people have put forward, this isn't my idea, is to take each spider in your ZX diagram, and by interpreting this ZX diagram as a measurement pattern, you can, if you like, unmerge the initialization and measurements of each spider, so that each spider now corresponds to a qubit, and the links between qubits now correspond to entanglement operations. Sorry, the link between each spider corresponds to an entanglement operation. So on the right here, we have exactly the kind of measurement pattern style implementation that you'd get from the ZX diagram on the left. However, while quite a few people have thought about this kind of implementation, the problem that you get, as with all of these measurement pattern style implementations, is that in general, even accounting for the ability to perform corrections, you can't do the ZX diagram deterministically. So for example, if we have the ZX diagram that we have on the right here, if we don't have the Pauli here and we just want to perform this as is, obviously this is not injective on inputs, and therefore even with corrections, you can't perform this deterministically. And so kind of piggybacking off of the ideas of MBQC, we can prove that this translation works deterministically for bipartite ZX diagrams which satisfy some properties such as being graph-like and having some G-flow. You can actually relax the bipartite part of this a bit. This is quite a lot of conditions, which again I don't really want to go fully into, but happily you can satisfy these conditions for any isometry which is in a particular gate set as a circuit to begin with. The idea for all of this, but piggybacks purely off of the work that people have done in MBQC in the last few years. And at the moment, what we're doing is comparing the results for how small the kind of braiding diagrams are to alternative methods of doing this. And I think that's me done. I see a lot of notifications, so.
Let's thank the speaker. I have a question.
Go for it.
Yeah, you give this like a assignment of like these braiding diagrams to ZX stuff. And you say this like this isn't the functor. Is that correct? Is this like an assignment in the other direction? Like, is there like a functor from ZX to like some whatever fusion category?
Yeah. So strictly speaking, there is a functor from the modular tensor category to the category of finite dimensional vector spaces, but it doesn't give the things that I have on the right, because these things are only the subspaces in the subspaces which don't have which are corresponding to the one objects by the interpretation functor. So you can define a functor which does take you to the category of ZX diagrams. So in general, it won't be just qubit ZX, right? Because you'll have some dimensionality problems. But in general, yeah, you can easily define a functor from the surface code MTC to a ZX diagram.
In the other direction, though, is there a functor going from ZX diagrams to?
Yeah. So so you can go from qubit ZX diagrams back to modular tensor categories in such a manner that the assignment will then take you back to the original ZX diagram that you started with. So basically what you could do is you can say for any green phased spider with an arbitrary number of input and output legs, you take this to being some combination of fusions and splits, which are just the inverse of this. Obviously, this won't be deterministic because of the measurement problem. But if you're just working in pure state stuff, then yeah, you can define such a functor. I have some diagrams of this in the paper that I've been writing, which I can show you.
This is a functor, though, at least from ZX, from pure.
Yeah, everything composes properly. Yeah.
Okay, thank you.
Unless I've missed something. But so this functor and trying to do compilation functorially is in general like a bad idea, like for practical purposes, right? I know that's not what you asked, but I just want to say for for the audience that in general, when you're trying to perform compilation, you want everything to be, or you want to try to optimize everything as much as possible. And this in general means that the translation from high level to low level, or from different languages, you want it to be very context sensitive. It's possible that there is a way of describing this functorially, but like my naive interpretation of that would be that you don't want it to be functorial, that you want it to be dependent on what's before and after it, and maybe next to it as well.
Any more questions?
Did you go to slide 50 something? Sorry, I don't know the number.
I have slides 50 and 51.
Oh, okay. Slide 49? I think it's 49.
Yeah.
Yeah, when you were commenting on this slide, sorry.
Yeah, I can go into a bit more detail about what's going on here.
Yeah.
So on the left-hand side, we have some ZX diagram made out of spiders and Hadamard down here. And by the assignment that we dictated earlier, we're taking each spider and saying this spider is now a qubit. If the spider has an input and an output, then we don't have to initialize or measure out that qubit, which is what's happening with the top one here, right? So we have the dual qubit having some open wires here, and then we're performing the entangling operations here, and then afterwards we're performing the phase on it, and then having some more open wires at the end. So that's the case when you have an input and an output, and that's the straightforward one. But by contrast, we have this wee green spider here, where we're both initializing the spider and measuring it out at the end, and we're only using it to perform the entanglement required on left, right, and bottom. And the green spiders will correspond to dual qubits, and the red spiders correspond to primal qubits. And the motivation behind this is to avoid, by doing this translation rather than trying to go kind of in a gate-based fashion, you avoid having to induce all these extra type exchanges and extra kind of ancillas and so on required to convert. Because this is heuristic, and I'm still in the middle of benchmarking some stuff, I can't like prove this to you, but there's a bit of work by some guys in Japan that I can link, and this is the sort of thing that Craig Gidney's been doing for a while as well.
I have one question about that. So you mentioned before that braiding, like if you do a C0, the braiding over then under is the same, or both are C0 and as if you did under then over. So so you're saying that in CX diagrams or in circuit notation, those would both be the same, but they are contextually quite different in the braided diagrams, in that based on context, like as you said, if you have a larger diagram, it does matter whether you braid over then under or under then over first, as to whether you can untangle. So that's one part I don't understand. Are you losing information, or are they?
I'm not sure I understand the question. So we have two different braiding operations, which happen to give the same assignment to the. They happen to have an assignment to the same linear map. I'm not sure I understand what you mean by context dependence.
Like say here, it's like as if you are twisting the black and teal wires together, and then if you were to then do another one, you twist in the opposite direction versus in the same direction. I think, are those operations the same?
You can work out that if you compose these and then move everything up to isotopy, then composition still works out. So you can show, for example, if you do this one followed by this one, then by isotopy you can pull the wires apart and unentangle it, which corresponds linear map wise to the two C knots in a row cancelling out.
May I just say that the point is that the representation of the ZX diagram as a braid diagram is not, it's not unique. So if you were to map it to one of them or map it to the one with the reverse crossings, you could in one case be consistent, in other case not be consistent with the context, with the braids surrounding it. I think this is the point she's making.
Right.
So you said that there was a kind of functor from the ZX diagrams to the modular tensor category, but if there was, then there'll be a particular assignment of that choice. You could either have the crossings or the reverse crossings for this particular C0 gate.
Right.
So for example, if you decided to implement the C0 as the one shown in this diagram, and if you applied it twice, then you wouldn't be getting the identity because it would be doubly tangled.
Right. Sure. I think that the particular functor which I described, that is going from each spider individually, avoids that problem because
well, I think also the category that you start with is not a free braided category, right? There's
I was going to
more
ask
equations than just what would hold by isotopy.
It could be that the quadruple twist is the identity, for example. I was going to ask you about that, Alex. Could you say a bit more about that multi-tensor category for surface codes, the one with the E, EM, and epsilon? Sure. What does the braiding look like? These are all up to isomorphism. What does that mean exactly? I just want to get an idea of what the structure is.
So it has. So I believe it is free in the sense that you can apply any braids to any objects, and this is natural and all the rest of it. In the category itself, the quadruple braided will not be equal, right? This is just by virtue of the interpretation. I don't believe there's some rule in the category itself which defines these as being equal.
Let me just say
maybe that does put the kibosh on the functor back again. I'm not sure. I need to think about that.
Okay. Can I just ask if this particular category has an algebraic origin, for example, as coming from representations of algebra?
Yeah, it's got a very straightforwardly. So it's you take the Drinfeld double. The Drinfeld double of Z2, and then I want to say that this is the representation category of that. Although, in that sense, if that was entirely true, then you'd have that the objects are vector spaces, right? But that's not the case. But it's something like the representation category of the Drinfeld double of Z2.
Yeah, I think at the point, a lot of information buried in the isomorphisms. So there could be a co-cycle or something in there. Maybe I can discuss that with you, what the actual structure is.
Yeah, sure.
You can't tell, it depends on the exact nature of the isomorphisms. And there's also the braiding is implicit in there as well. For example, you take E tensor M, you identify it by one isomorphism with epsilon, and then you can also unidentify it with M tensor C. But the composition of those maps is the braiding. But unless you know what the isomorphisms look like, you can't really say much. So you need to have a lot more detail. Yeah,
no, that's true. In particular, something which a lot of mathematical physicists do is they make this thing skeletal, which I strongly dislike because the isomorphisms are extremely important.
Yeah, okay.
There are some. So there's a question in the chat about what kind of anions these correspond to, So these aren't Ising anyons, although the gapped boundaries that we have here, 1 plus E and 1 plus M, the fusion algebra of these is extremely similar to if you were to say that each of these strings corresponds to 2 Ising anyons, which is related to twists which you can perform on the surface code, which we can maybe discuss at some other time. Oh yeah, you actually mentioned this in the chat. I just didn't read that far down. Okay. Does anyone else have any more questions? Cool. I think I'll stop sharing then.